All right. Well, welcome everyone. We're doing a quick session on how to best deploy ScaleIO in a VMware environment. My name is David Stemerdink, and I run the SDS pre-sales business in EMEA. So what we'll go through in this quick session is an overview of the types of SDS that we see in the space, a quick wrap up of what ScaleIO actually is, what it looks like, and how it works, so that we're on a base level of knowledge. And we'll actually go into a couple of details that you'll find in our best practice guides concerning the network configurations that you need to put in place if you want to get optimal results, as well as some server design considerations. So, when we actually start to look at the types of SDS in the market and where we play as a company, right, is the Type 2 and Type 3 types of deployments of SDS in VMware. Welcome. So the two types that we identify is what we call a vertically integrated stack with VMware vSAN obviously being there. Which has a lot of benefits, right? So it's fully integrated, it's very easy to manage, easy to deploy, it's managed from a VM perspective or a workload perspective, and it's very much optimized, again, for VMware environments. The other type of SDS that we see approaches this from a slightly different angle, where we look at horizontal solutions. So a horizontal stack, meaning that software-defined storage is treated as a separate platform. The networking is treated as a platform. Think of HCI kind of things. And obviously the workload visualization is treated as a different platform. So we have companies either choosing to do one or the other, or a mix of both actually, depending on their needs, right? And as a company, we actually own, I would say, two of the market-leading products in that particular space. So, looking at what ScaleIO actually is, right? It's a relatively easy to understand solution that addresses this from a software perspective. So in order to actually consume storage, you would install what we call a ScaleIO data client in your ESX server, which operates at the kernel level, right? So this is just the device driver. Think of it as an HBA that exposes a volume, right? We're making it sound simple. There's a lot of stuff going on in the background, but the key is we keep it simple, right? The second component is what we call our ScaleIO data server. This is basically an application that runs in user space. In this case, we run it inside of a VM in VMware. And we use this as kind of like a storage controller, right? So you deploy a couple of these, and just like with vSAN, you need at least 3 to start. But we can actually scale to about 1,024 nodes in a single system. That's the only job that these two elements have, right? One is consuming storage and transacting application I/O. The other is actually building your scale-out storage array. Obviously, there's some management in there. Won't go into too much detail. Management is highly available. It's outside of the data path, and we've made sure to keep it very, very lightweight. Right, that's the key thing that we've did with everything, is making sure that we have as little as possible impact on the actual platform that we run on. So, where do we deploy? We deploy on any x86, right? Not exclusive to VMware. We support Windows, we support Linux as bare metal systems to run both the client and the data server on, and we support a very broad range of hypervisors, right? And there you will actually find some of the differences, right? Because we support this very broad ecosystem. We let you manage this from a storage perspective, not so much workload, although there's some progress being made there as well. On the integration side, OpenStack is a key player, VMware is a key player, but we're also heavily invested in supporting the Docker and Mesos and all that new kind of stuff, platforms, which you'll find some very good resources on our code community site as well. And there's more. So, what does this actually look like, right? What are we talking about when we deploy this in VMware? As you see, we have our client just installed inside the hypervisor. It's exposing a volume, just as you're used to with a, I would say, a fiber channel controller. Almost as an iSCSI, I would say, although it's a little bit different. And applications can access ScaleIO volumes being presented through this particular client. Now, where we source the actual storage, where the SDS lives, in this case, we actually run it inside of one of our VMs, but that's not exclusive, right? So these SDS servers could also be running on some Linux boxes sitting outside of the ESX cluster, or some Windows boxes sitting outside the ESX cluster, and they could all be sharing this very big resource pool of hardware and presenting scale-out storage out to VMware and all the other environments, right? So we try to build this as a solution that customers can use for multiple application areas, where VMware is definitely one of our key adopters, right? So about 80% of ScaleIO being used globally is being used in VMware, and we're talking about 600 petabytes as of today. Right. The way the system works is from a conceptual point of view, very easy, as it's fully scale out. Which means that our data client has some intelligence in it, so it knows exactly where to go to touch a certain point of data, right? So there's no management getting in the way. It can go there directly. It can do these operations in parallel. That's how we kind of design the product. And when we look at this operates in a full mesh, right? So all the elements can talk to each other. There's no hotspots to manage, as all the disk resources actually work in conjunction. This is a kind of a big architectural advantage that we have, because due to this architecture and this being native to the solution, that means that there's very little movement of stuff going on in the background, right? Everything's distributed, so the load is always even, which means that you don't need to move data blocks around. If there is a higher load on a certain segment or the other, everything just stays in place and it will work optimally. Okay. The way that we then protect data is by creating a secondary copy of a data slice. And today, our data slices are about 1 meg in size, and they're distributed through what we call a mesh mirror algorithm. That means that the failure domain is the server node, and this is our basic protection, right? So any volume that is being presented, or VMFS data store, is actually living on all the disks, on all the servers in the environment in a mesh algorithm. The key here is to try and make sure that we have an even load on all the disk devices in the system. And as the environment gets bigger, this becomes easier and easier and easier to maintain for us. Now, to protect data, we obviously have to create some secondary copies of these data blocks, and a system that makes sure that these data blocks are, again, evenly distributed, and obviously not having a primary and secondary copy on the same node. That would be a bad thing, right? So whenever there's a failure, and I don't think the animation is showing quite what I wanted to know. Oh, there we go. All the remaining nodes will actually participate in this restore operation, right? So even for restoring, there will not be a single hotspot. There's never a single node that's being tasked more than the other ones. So as you grow the system, you don't get just more capacity and more performance, but it also starts to rebuild faster and faster and faster, right? And it's dramatically fast. So rebuilding several terabytes can be done in a matter of minutes. The infrastructure that you accommodate, if you put to that, is really the deciding factor in how quickly you can rebuild, right? This is completely different from traditional old school storage. So now that we have that basic understanding, let's look at some networking considerations that we've put in place to make sure that you are actually able to get these results. So I hope you can make some sense of this diagram. what I basically want to show is the way that we actually mirror the data, right? So we have a notion of different networking profiles that we can apply. One network profile will actually allow you to transact all types of activities on a single interface. And these activities relate to, obviously, application I/O that's being driven. But we also have the notion of what we call a backend network. So that's the kind of work that a traditional storage system would typically do, right? So that's making sure that we create secondary copies of data, making sure that if you have a failure, that rebuilds occur on that network, or if you're just simply adding or removing resources, that you use that dedicated network to run that kind of activity. The benefit of being able to control this is obviously that you can build a network architecture that's going to give you a very predictable and responsive type of behavior, even when you're growing, shrinking, or dealing with failures in the cluster. So the way data actually transacts is that an application writes this to the volume that's being managed by the data client. The data client will always just send either one read or one write request, and the data servers will take care of duplicating that write on your network. So that's a very basic premise. So again, when you put this against traditional storage, it functions in a similar manner, right? So you write against the volume, and the storage system will make sure that it's secured in two locations. Typically, that's two controllers with some write caching, destage the disk. This is a very similar approach. So when we actually look at the traffic types, generally we see that the application traffic that we put on a system is actually not all that aggressive. So even if you're doing tons of IOs, typically that client is not the biggest impact on operations that can actually affect how the network is being used. Typically, when we see when there's real pressure on the environment is when something goes bump in the night, right? You have a disk failure or a node failure or a rack failure. That's where you're really going to need that networking bandwidth in order to make sure that you can recover from that very quickly. And because we are a parallel many-to-many operation in that, you can actually start to drive very high levels of bandwidth utilization, which is obviously fine. But what you want to make sure is that this activity doesn't have any impact on running applications. Now, there's a couple of things that we can do from a I/O flow control, quality of service setting, or even setting some limitations for all these processes. But we can extend that by saying, okay, I want to use a dedicated interface to actually run a certain traffic type. Typically, we talk about this with customers when you have to commit to a certain SLA for a storage service, for an application kind of profile, where you want to make sure that even when you are having issues in the environment, you'll be hitting that SLA, right? That's where isolation can give you some advantage over just doing quality of service. So what we've also done in our protocol, which is again something that we developed, is that we've included the capability natively to do things like multipathing, right? So adding more links to a system will actually allow you to drive higher levels of throughput, where we can scale that up from 1 to 4 connections. The other use case, obviously, is that this also provides network path redundancy in the actual system. So even if you have a very simple setup of two layer 2 network connections, ScaleIO will do the multipathing and failover for you. Having said that, if you want to implement network resiliency, so implement any kind of LACP functionality, that's something that's obviously also fully supported, as we're pretty agnostic to that. We've seen so far that there's a minor performance difference in using LACP versus our native stack, where we're getting about 10% more effective bandwidth out of links when we do native multipathing of ScaleIO. But that's getting into very nitty-gritty levels where you typically only see that if you're running at top-level load in a system. Our protocol will adhere just to standard IP rules, right? So there's nothing too magical about it. It looks kind of like iSCSI, but it's not. It's SCSI over IP using our own protocol, and it fully supports layer 2 and layer 3 networks. So if you needed to expand that, that's fine. We've also added support for IPv version 6, both on the management plane side, but also for the actual storage system itself. So depending where you are in your environment and where you want to go, you're free to use either of these technology sets. Jumbo frames is something that was highly recommended when we all started out with iSCSI. I think we've come back from that a bit. Certainly we have. So we see that the actual benefit of running jumbo frames over a network is not always that big, but it does add substantial complexity in an environment, which can also mean that it gets more difficult to actually troubleshoot if you have a single element misconfigured in an environment. So our recommendation on the networking side is, particularly when you start to scale to hundreds of nodes, is keep it simple. Right, so unless there's a real requirement for you to drive that additional 10% bandwidth out of the environment, we typically say, oh, well, don't bother with it, just stick to the standards. That's going to save you a lot of headache in future. And obviously, redundant networking, highly advised. Either using networking technology or using our stuff, it will save you a lot of headache. So, networking, flat, has a very easy point of actually adopting this. Managing it is very simple. There's no additional hops when you go to different racks, all that stuff, which is nice. But scaling this becomes a bit of a problem, right? You can probably do 2 racks, maybe up to 4 if you get some really big switches. After that, it becomes a nightmare to scale well, right? So one of the issues there is when you get multiple switches connected in a fabric, you'll get different hops between them. You'll have different networking bandwidths between them, which means that you're going to have a system that is not very predictable. And that's exactly where we want to get. We want to get to a system that scales easily and delivers predictable performance as we go. And this is why we would very much prefer you, even if you're starting out not too big, to consider things like spine leaf architecture, right? This will actually allow us to grow the system from a limited amount of nodes all the way up to our maximum, which is currently 1024, without changing the actual network topology. So that means that every node has a similar path from one rack to the other. The amount of hops is the same, the bandwidth is the same, which means that you get something that is very predictable in nature. So, when we look at some of the things that come with using network redundancy, right? There's different things that we can put in place. Obviously, when we use our native capability to run multiple IP interfaces, that means that you have to manage more IP interfaces. So some customers will actually say, okay, well, I don't want to get in that game. I want to keep that IP planning as simple as possible, and I'll just do network redundancy because I'm also running applications on those same interfaces which don't do your fancy stuff, right? So, okay. So we'll use LACP or any kind of bonding technology to make that happen as well, and get away with having just a single IP interface for a client or data server that sits on a node, and configure our network to provide redundancy. What we've tested and documented is that we can work with single switch lag aggregates or multi-switch MLAGs to provide resilience. However, when we do configure MLAG, there's some things that you need to check, right? what we typically see is when you implement an MLAG link is that the failover time for detecting an error with any of these links is actually not quite where we want it to be at. So the timeout is a little bit set too high, which can cause some issues with transacting data operations. So we would ask you to reconfigure that and make sure that the timing on the failovers is reduced from its standard setting to pretty much as low as you can get it, depending on the switch vendor. This take care of two main issues. Like I said, one is actually transacting application I/O that could be stuck for some time. The other advantage is that our management is also quite sensitive to disruptions in the network, and it will really like you to actually do this when you configure an MLAG. So, a quick wrap up of the networking design conclusions, and you'll find a lot more in our best practice guide, is to keep it simple. Make a conscious choice if you really want to use jumbo frames, right? What we typically see is we get about 10% more bandwidth through a link. So for, let's say, a 10 gig link, that would mean that you'd go from 1.1 gigabyte per second per link to 1.2 and a half. That's not all that much, but it introduces severe additional complexity. Where lags and MLAGs are nice to provide a very simple IP plan, they also have one other downside, which is that you're actually stuck with one logical interface into a node, right? So your network stack might be redundant, but you're using a single IP route to that particular system. So if there's a routing issue or somebody types in a wrong IP address, you could get into some issues there. So even if you would use MLAG because you're using those two links to do different jobs, so you have your storage there and you also have applications there, it could still be worth considering using redundant IP configs on your particular node. And with redundant IP, we actually mean that you need to have like two ranges in order to make that work. Backend networking can be very interesting, again, when you're trying to design an environment that's supposed to deliver a certain type of performance all day long, no matter what happens to it. This is where the dedicated backend networking can help you out there, right? And make sure that you use a networking topology that matches your projections. So if you are not going to grow in a likely manner beyond, let's say, 2 racks, flat networking is absolutely fine. However, if you're foreseeing that this platform that you're building has the potential to grow beyond that, then starting out with a leaf spine architecture will save you a lot of headache in future. Okay. So, as a final part of this, we'll actually have a look at some best practices that we'd like to share with you for actually designing a server that will run this this software in an HCI manner. Starting off with some numbers, right? So when we consider ScaleIO and the impact that we have, again, we try to minimize it. And I think we've did a pretty good job. And we will actually allow you to run the system in 2 different modes, right? So a default mode that uses the bare minimum of resources, or if you're projected to need more performance, you can just simply flip a switch, so to say, and enable what we call a high performance profile. What do we get with these, right? So when we run our data client in a standard networking profile, you can expect to do about 100,000 IOPS. 200,000, oh sorry, SDS, let me switch that around. So the standard profile on the SDS side, you'll be able to do about 100,000 IOPS from that particular node, right? If we would actually enable the high performance profile, that number basically doubles. Data clients, same story. Because the data client only has to take care of single I operations where the data server has to duplicate these. You can actually see that it is able to drive more performance even with the standard profile. And keep in mind, these numbers are all scale out, right? So the impact of running either or of these profiles really comes down to what happens in the background. With our default profile, we will actually allow a data client or a data server to issue its operations over 4 logical threads. So not 4 cores, but 4 threads that we assign, or not assign, but we unlock. When we go to high performance, that basically doubles to 8 logical threads. So for I would say a modern CPU, that would basically mean that you see that about 11% is used for running ScaleIO on one of these systems, with some pretty impressive numbers, I would say. In reality, we rarely see customers hit that high mark. So in reality, most of the day, we see about 5% of the CPU utilization in a system being allocated to ScaleIO, which is typically quite acceptable, I would say. So the other part of actually that is probably more relevant in a VMware environment is actually, okay guys, how much memory do you actually need to make this happen? Because that's where my constraint typically is for actually scaling an environment. So when we look at that, and we look at the core ScaleIO elements, and we would actually scale the system up all the way through our maximum number of nodes and the maximum amount of capacity we can manage today. That needs about 512 megs of memory on a server to actually manage that. And that is also true for the SDS. So the SDS would also need a similar amount of memory for this maximum size configuration. Data client can get away with even less. So you can map about a petabyte of volume space, and we don't need about 2 megabytes of that to manage that. So some other use cases for memory would be to enable caching. And with caching, you can start out with a very small amount, 128 megabytes, and go all the way up to 300 gigs per node today. Again, I'm not sure you want to allocate 300 gigs of your ESX server's memory to caching, but we can. So those are the basic elements. However, when you look back to about that third slide that we had, we actually need to run some of the ScaleIO elements in a VM, which means that we need some memory there on that VM side. And there, 4 gigs is fine, and you can increase that as you want. Some performance numbers. Because we don't fully run natively and we need to go through that, you will actually see that the performance is slightly less. However, if we put the controller into direct path I/O mode, we'll get about 10 to 15% more performance. The main reason, however, for using direct path I/O is not so much around the performance increase, but also about responsiveness when we deal with failures. So it's a lot quicker to respond. So, quick wrap up. When you're designing a server, about 4 gigs of memory overhead per node will actually suit ScaleIO fine. You can increase that to 8 for all I care. That's all we need. 5 to 10% of the CPU should be allocated or reserved, or however you want to look at that, as part of your sizing exercise for running the elements, and that's all you need. If you want to use direct path I/O mode, that means that we need a dedicated controller for that, so a SATA DOM or any other kind of device will actually do. Use redundant networking, and if you're looking at some futures, NVDIMMs are going to unlock some very cool things in future. And all-flash is blazingly fast with ScaleIO. So, I would like to thank you very much for attending this session today, and I'll be out here if you have any further questions. Thank you.